Hello students, let's start the very first topic from the subject quantitative reasoning 1. What is quantitative reasoning 1? Quantitative reasoning is the ability to use mathematical concepts and skills to analyze real world problems. So before we dive deep into the lecture series, let's start with the basic concept of number system and basic arithmetic operations. So here are few of the learning outcomes. The first is understanding of fundamental operations. When it says fundamental, that means addition, subtraction, multiplication, and division. Then students would be able to apply those operations using PEMDAS, or more formally known as BODMAS. Then they would be having few basic mental arithmetic calculations, and then we are going to solve number of questions that would involve arithmetic operations. So what are numbers? You might have experienced that whenever you need to determine the population of the country, you need to express that in the form of numbers. Similarly, if some student is like learning or being enrolled in any of the semester, so in order to express that number of months left for the study or number of months left in the final exams, they need to express that in a numerical form or in a quantitative manner. Similarly, if a person owns a charity house with 800 occupants, how much food needs to be prepared? So in order to address these questions, we don't use English verbs or English words like more, much, a lot. We express them in some number format or in the form of numerals, for which we need a number system. So if we start to see where this system begin from, in the number system, the largest set is the set of real numbers. That can be like we can say that the universe is so real numbers are as huge as universe. When we categorize real numbers into two categories, we have rational numbers and irrational numbers. So let's study rational numbers first. Any number which is written in the form of a quotient of two integers. For instance, if I'm writing p over q, where p is integer and q is also an integer, provided that q is not equals to 0, then the number come out is a rational number. For instance, if I write 10 over 2, the quotient would be 5, which is purely a rational number. That means a rational number is a whole number or a terminating decimal number. Let's take another example. If I say 5 is divided by 2, in that case the quotient is 2.5, which is again a terminating decimal number. So rational numbers are those numbers which are formed when an integer is divided by an integer, provided that the denominator is not 0. Under the category of rational numbers, we have further classifications of numbers as integers. So integers are numbers that have positive or negative signs. If you want to express the quantity of number of students in a classroom, that is again integer. If you want to express the temperature of any city, that is again an integer. So integer are the numbers that are either positive or negative. They are denoted by positive z or negative z. Under the category of integers, we have whole numbers. So whole numbers begin from 0. If you have seen a number line, on the positive side of a number line, we have all positive numbers, and on the left side of 0, we have all negative numbers. So this combination of positive and negative numbers make integers. And when we only focus on the numbers beginning from 0 and onwards at the right hand side of a number line, they make whole numbers. Under the category of whole numbers, we have natural numbers. So natural numbers are simply numbers beginning from positive 1, and they are infinite. As we move along the number line on the right side of 0, we are approaching towards the larger numbers that make the natural numbers. Now, these were all the terminating rational numbers. Let me explain you the non-terminating decimal numbers. For instance, if I'm given a certain number, which is, for instance, if I'm getting 4 divided by 3, and I divide them using a calculator, and I get the answer as in this form, where after a decimal there is the same number being repeated many times, I can write it as 1.3, and over 3 I can put this little bar, or I can write it as 1.3 with dot over 3. That indicates that this is a non-terminating decimal number, and since the same number is being repeated many times, it again comes under the category of rational numbers. So rational numbers have non-terminating decimal numbers and terminating decimal numbers. So this is the example of non-terminating decimal number. Similarly, if you get a question like 7 over 6, and after dividing these both numbers, we get the number in the form, that same number being repeated many times, you can write it as 1.6 bar, or similarly you can write it as 1.6 dot, which is again one of the forms of writing a non-terminating rational number. We can say that 1.666 is a recurring rational number because same number is repeated many times after the decimal. These were all the classifications of rational numbers. Now, if we come to irrational numbers, at the right side of the screen, you can see that all the numbers which cannot be expressed as a fraction of two integers, as we express rational numbers, we cannot express irrational numbers in the form of p over q. Irrational numbers are denoted by q dash or q prime. They cannot be written as p over q. Take the example of square root of 2. If you use calculator, you'll see that square root of 2 may result in some non-terminating, non-recurring numbers which are not same after the decimal, and you cannot express them as a fraction. 1.414 and dot 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 indicates that there are many numbers after 4, and you cannot remove, even if you remove this decimal, you may have plenty of numbers in the denominator. So you don't have like any integer form of this irrational number. That's why irrational numbers can't be expressed as P over Q. Similarly, if we take the example of pi, which is written as 3.412, you cannot express pi as a fraction. Like many times we have seen that people write pi as 3.412, and when I remove its decimal sign, I may have multiples of 10, but I cannot express it as some whole number. So this is again a rational number. Sorry, irrational number. Let's move to the next slide. This is the set form of real numbers where they have expressed the categories and how they are denoted. Rational numbers are denoted by Q, integers are denoted by capital Z, whole numbers as W, and natural numbers as N. Irrational numbers are denoted by Q prime or Q bar. Then we all know that a number line is a horizontal line where 0 is basically a point of division that divides positive numbers and negative numbers. And at the right side of 0, we have all positive numbers. Over here, we have all positive numbers, and at the left side of 0, we have all negative numbers. The last number on both the sides is infinity. So we can always use number line as a graph to plot any point on the Cartesian plane. Next we have is hieroglyphic numeral system. When number system wasn't evolved, people used to have these symbols to express numbers, and these are, for one, they used to have one stroke. So in order to write 2, that means in order to write any single digit, they need to put strokes. So for instance, if they have to write 5, so they need to put 5 straight strokes to express 5. Similarly, if they want to express 9, they need to put 9 strokes until a symbol for 2-digit was evolved, that is this hump. Because in number system, the numbers are keep evolving. So in order to express a 2-digit number, they needed to have something for which they developed another symbol, that is hump. Over here, this is for 2-digit number. So if someone has to express any 2-digit number, for instance 20, they need to draw 2 humps like this. 20 is basically 2 tens, so they need to draw 2 humps. Similarly, if anyone wants to express 40, so for 40 they need to have 4 tens, that means 4 humps. This was only valid for 10 and multiples of 10. They were again in problem when they had to express some non-multiple of 10 number like 99. Now in order to express 99, they need to have 9 humps plus 9 strokes. that makes a huge number, then it was again a problem for mathematicians until a new symbol was evolved, which was a coil that is used to express 100. So for 3-digit number, they used to draw coils. And this keeps on happening. For 1,000, they had this bent arrow. Then for 10,000, they have this straight bar, little flicked upward. For 100,000, they have these two symbols evolved. This really put all the students into trouble because it was really difficult for them to memorize and to express large numbers in the form of symbols. Thanks to base 10 system, thanks to number system that was evolved after a long period of time, and this made the problem like solved. People were happier using this positional number system, and this is basically dividing numbers into groups of periods. The first period, which is at the rightmost side of the number, is named as units. Moving towards left, the period was named as thousands, then millions, then billions, and finally trillions. And under each period, there were three similar headings of ones, tens, and hundreds. Ones, tens, and hundreds. So for instance, if someone has gotten only a 3-digit number like this, so starting from the extreme right, the person has to name it as 1, then this would be named as 10, and finally this would be named as 100. So they are going to read them as 341. Similarly, if someone has gotten more than 3 numbers like 4 and 8, they are 5 digits. So now the period units is over and they are moving towards left. After 100, it's 1000. And then to the extreme left, it's 10,000. Because this green part lies in 1000 category. So now they would name these digits as 84. What's the period name? Period name is 1000. So they are going to name them as 84,341. This is how reading and writing became easier. Let's practice few more questions. People can also remember them as, if we have like the 6 digits. Now, in order to read those 6 digits, they need to first give them periods. The first period is units, and the second period is thousands. After the period has been given, they will write them as ones, tens, and hundreds. Similarly, in each period, in the next period, it would be named as ones, tens, and hundreds. So now starting reading from the extreme left number, which is 8, under the umbrella of H. So it would be read as 884, then the period name, which is 1000. So they would read them as 884,130. I hope I'm understood. Now let's practice any one of these given questions. Let's start with number 2. Over here, there are, let's write them first. This is 36, and then we have 8 zeros, 8 zeros, and then we have 1. So recalling the process that was explained in the previous slide, we'll put them under the periods. This is units. Let me show the next period as thousands. The next period, millions. And finally, the last period as billions. Recall, I told you that in each period there are 3 categories, starting from extreme right, which is ones, and ending on 100. So in the category of billion, there is no third digit. That means over here you have to name it as tens and ones. Similarly, if I move to the category of million, in which all the numbers are 0, we don't need to mention zeros. Similarly, in thousands, again, all the numbers are 0, so we don't need to mention them. And finally, the last digit is 1. So we would read them as 36 billion and 1. This is how the number is read. I hope this explanation is enough and you would be able to solve next 3 parts. Let's move to the next slide, which is about basic operations on real numbers. The first is addition, then we have multiplication, then we have subtraction, and finally we have division. So the first question, let's read it. The number of nursing and related care facilities in the United States in 1971 was 22,004. In 1978, the number was 18,722. What was the total? Over here, this total indicates that you have to use the operation of addition, because when the number total, when the word total and sum appears in the question, that means addition is required. So in this question, you simply need to add the population or the related care facilities given in 1971, which is 22,004, and the next is 18,722. Moving to the next question. Now, next 2 questions are from fractions and decimal parts. Again, over here, we need to read the question first. Let's start with the extreme left question. Sarah baked 2 pies for a family gathering. She served this of 1 pie and this of other pie. What fraction of pie did Sarah serve in total? Again, you can focus on the last word, which is total. In this question, again, you need to add these 2 fractions. 2 over 3, 2 over 3 plus 3 over 4. Over here, the denominators are different, so we need to take the LCM. In order to make 3 12, we need to multiply it by 4. Similarly, in 4, we need to multiply it by 3 in order to make it 12. So now the numerators are 8 and 9. You simply need to add them to come to the final answer. So Sarah has used 17 over 12 in total of pi. Moving to the next question. Now again in this question, you need to identify which operation is being asked. Someone had this amount in the wallet, this has been spent, and this on the book. On this, out of this amount, certain portion is spent on groceries and certain portion is spent on books. So we need to check the spent amount first. In order to check the spent amount, we need to add these both values because they were spent in total to buy something. And then it has been asked to find the amount Sarah left in her wallet. So when the word left comes in some question, that means they are asking you to use difference as operation. So this would be, in this question, you need to find the amount Sarah had left with, because Sarah had already spent two parts of the amount. So you need to add the two parts of the amount and then you would subtract the sum of it from the total amount. This is how you would get the answer. Let's see the next question. Again, the next question are from two different parts, which is fraction and decimal. Again, over here, you need to see they have asked the difference. Over here, it's again difference. That means you need to put subtraction as operation over here. Right. This is the next question in which Hannah dedicates 3 hours each day to study. If she commits to study consistently for half a month, now she's studying 3 hours, and over here she's deciding to continue to study for half a month. How many hours will she study in total? Now we need to find number of hours she'll be studying. So in order to find how many hours are there in half a month, so first you need to check how many days are there in a month. So for instance, there are 24 in one day, we have 24 hours. And if a month has 30 days, we need to take product of 30 by 24 to find out number of hours. Since Sarah is studying for half a month, we can directly calculate number of hours for half a month, because in one day she's studying only 3 hours. So we don't need this step. We'll directly come to this step where she's studying 3 hours for 15 days. So if in one day she's studying 3 hours, for next 15 days, she's going to study for 45 hours. Moving to the next question. Again, from few different categories, fractions and decimal numbers, the same operation of multiplication is given. I hope you would be able to solve these questions. The next and last operation is division, where you are given a number in which if the number is written under this root, its dividend, the number with which you are dividing is divisor, and the answer you are getting is quotient. For example, if you are given 17 upon 6. So 17 makes the dividend. 6 makes the divisor that I'm showing with different color. And when you divide them both, you would get answer as quotient. Moving to the next slide. So let's do one from decimal parts. Tom has 45.60 in his savings account. He wants to buy a toy that costs 12.75. How many times can Tom buy the toy? So in this question, they are asking that the cost of a single toy is this 12.75. So if he buys one toy, he has to pay 12.75 once. For one toy, he has to pay 12.75. For two toys, he have to pay the same amount two times. For three toys, he has to pay the same amount thrice. So they don't know how many times they have to pay the same amount, or in order to buy more toys, how many times they have to pay the same amount. So in this type of question, they will simply divide the given value $45.60 by 12.75 to check how many toys can Tom buy out of this amount. Let's do the next one. PEMDAS, the order of operation. Here you have to use parentheses, exponents, multiplication, division, addition, finally subtraction to solve a simple question. Let's do one example from this part. Let's take question number 2, where you are asked to solve a given expression using PEMDAS. So in PEMDAS, we have to open bracket first. So let's open the bracket first, which is parenthesis. So when I'll open this bracket, I need to perform the given operation inside it. So the given operation inside it is product. So this would be 12 would be written as it is. And when I expand this bracket, this would become 8 plus 6. This part is done. Since in this question we don't have any exponent, we are not using this E part as there is no exponent given in this question. Multiplication was already done under the bracket. Divide is again not given in this question. Let's check addition. Yes. So you can see that 6 is having plus sign and 12 is also having the plus sign. So we'll add them both first. So 12 and 6 makes 18. Minus 8 would be copied down as it is. This is how addition is done. And finally, the last step requires subtraction. So we'll subtract 18 and 8 and we would get 10 as answer. This is how PEMDAS is going to be used for these huge expressions when number of operations are given in a single question. I hope this is understood. Use this given information to solve the rest of the questions. These are more questions given for your practices. Thank you. I hope this presentation would be helpful to gain information and knowledge of
the topic number system and basic arithmetic operation. Thank you.